You really don't know the condition of any of the sensors controlling fuel calculations. And you don't know how the O2 is looking. So let's talk about scan data. After this correction for a lean mixture has been made and completed, where will the changes show up in scan data? What are you going to look at, and what's going to be the clues? Well, in this particular case, in this example, the long term will increase. The short term will be switching around 0. The O2 will be switching normal, and air-fuel ratio will be 14.7. Let's go through and see why all that's possible. But remember, if the correction is not possible, we're going to set a code. In this case, we're going to set a lean code. It's reporting lean on one bank, and if we have a 4-cylinder engine or an inline 6, there's probably on one bank. But remember, we have attached freeze frame. Quite often, lean codes set up at light load acceleration. Don't erase this code and lose your freeze frame before you've had a chance to understand what's going on. Remember, the car has already run, or the vehicle's already run, 2 consecutive tests back to back and failed the lean condition for 171 before it sets the code. It's already confirmed it's a valid code. Now, it may be there for the wrong reason, but it's there because the fuel mixture is wrong. Use the freeze frame to tell you where it happened and where you need to go back to verify the fix when you think you're done. Remember, this whole thing, we're trying to stress, reduce the number of comebacks. If this happens at light load cruise at 30 miles an hour, before you return the vehicle to the customer, you go look at light load cruise at 30 miles an hour and make sure the mixture looks normal, long-term, short-term, or normal in that range. This will tell you where to go and where to test it. Now, the other thing you're going to get when you start looking with some of the advanced diagnostics is a great many of your monitors may not run because they're blocked by the fuel system monitor. It's a horse race to who sets first. We're looking at mode 6 information. It can be in mode 5 in some vehicles, but most domestics have included mode 5 into mode 6, which is allowed by the EPA. In this particular case, we've got a red indication down there. It was for a TID 05, a SID 42, saying that the B1S1, Bank 1, Sensor 1 for fuel control, is lean to rich threshold voltage is not within range. The lean to rich threshold, the distance between lean and rich, is wrong. This would be an indication that you need to go investigate the oxygen sensor before you beat up on other stuff. Use mode 6 like this because there's not only this one, there's 50 other SIDs that relate to something to do with the oxygen sensor that fail to test. Now, you may find multiple problems and only part of it the oxygen sensor. That's also possible. But this is a good place to start in mode 6. Now, if we had a Chrysler instead of a GM, we'd, in that case, would have a TID 11, SID 81, the O2 half cycle counter, or one of the other 48 TIDs relating to something to do with it. Ford, TID 3, SID 01, B1S1 switch point voltage, or one of the other 12 TIDs and SIDs related to something to do with the oxygen sensor failed to test. Mode 6 will give us an idea of things we should check about the oxygen sensor as part of our diagnostics. And you're frequently going to find oxygen sensors that are failing something in mode 6 in addition to dirty injectors, low fuel pressure, low fuel volume, multiple problems. But remember, the oxygen sensor may look normal because of the correction. What you might be seeing is a slight shift leaner than normal. What we typically see is sharp-pointed tops on the positive going up and fairly long round ones on the bottom. Easier to go lean than it is rich. That's the usual indication. But it's going to show some type of shift in a lot of cases. But it's going to be switching back and forth normal. So remember, look at speed density systems, mass airflow systems, short-term, long-term fuel trim, and fuel system scan data. Remembering that a great deal of your fuel delivery system will show up nothing in scan data. Very few cars have fuel pressure. If you don't have fuel pressure, you have no idea if fuel pressure is good or bad on the vehicle. You have no idea if fuel delivery is sufficient. And remember, fuel delivery at idle is not the same as fuel delivery when the vehicle is operating under driving conditions. Drive the vehicle where it failed as indicated by phase frame. Let's start looking at what we should be looking at in scan data to verify these. What are the normal values for these readings? For wideband, we're going to save that to a whole program at the end of the program. But they are an important part of this that'll tell us a lot about them, and there's some special diagnostics we can do. But let's look at the other things. Let's say we doubt the MAP sensor. We want to verify the MAP sensor. What we need to start with is a test procedure. We test MAPs starting at engine off. Key on, engine off. This happens to be a GM. We expect a reading of 4.4 to 4.8 under 1,000 feet. Now, a word of caution. If your spec system doesn't show you tight specs like this, you can't rely on them. A lot of specs will read the same values that overlap between Long Beach and Denver, Colorado. If 5,000 foot spec overlaps with sea level spec, any at all, you cannot rely on them for effective testing. They still can be wrong. What we're trying to determine is if we start at zero vacuum or full manifold pressure, barometric pressure, we're going to wind up with a reasonable voltage. Then we're going to start the car up and idle it after it's warmed up and stabilized. Want to see what it reads. We like to look at a spec that includes vacuum because you cannot condemn a MAP sensor unless you verify engine vacuum. In this case, the expected engine vacuum is 20 inches. At that expected vacuum, we'll see 1.0 to 1.4 volts. If we see the 1.0 to 1.4, we can assume the vacuum is normal at the engine. We've solved problems. Remember, this is a load sensor. The lower the voltage, the lighter the load, the leaner the mixture. The higher the voltage, the higher the load, the richer the mixture. We have solved problems because at a specified vacuum, the voltage is either higher or lower, and some of them were deemed as unsolvable. They fixed everything, they cleaned everything, and all that was wrong is the MAP sensor was wrong. We've had MAP sensors that go wrong at a specific spot in a test drive and cause everything to go wrong. So verify it reads a correct voltage for the vacuum applied. If it doesn't, we need to verify it before we change it. Look to see if it's got reference voltage. In this case, it's a GM 4.9 to 5.1 at reference voltage, 5 volts at ground. If those two values are good and we cannot accurately read vacuum, make sure we have the vacuum source is to the sensor. Do we have plugged vacuum ports? We haven't seen very many lately, but they're still out there. We still run into them, and because they're rare, they frequently cause diagnostic problems. Do we have cracks in the vacuum hose or leaks? If that's all good, change the sensor. Now, if it's a mass airflow, same situation. Does it read right, key on engine off? Can we start off at no flow and read right? Then start the engine up, warm it up, get stable idle. Is it within specs? 0.6 to 0.9 volts. This happens to be a Ford. If you're hanging to either side of this, be leery of what's going on. Now, one other thing to mention. We have a lot of people tuning cars these days and tweaking with low restriction exhaust. Had someone call us up a while back and say, I got a truck, continuously fails mass airflow. Out of spec, the airflow's too high after I put a low restriction exhaust on. I says, good. The spec tells you your low restriction exhaust is working. You have more airflow. Be aware that engine modifications will change tight specifications like this. Always check for dirty mass airflow. We have frequent dirty mass airflows, all makes and models. Everybody says all the Fords are at fault, and there's a lot of dirty mass airflows on Fords, but they're not the only dirty mass airflows. Our dirty mass airflow check on a Ford we use voltage like this is to do a very sharp 2-second wide open throttle, use a lab scope, and make sure it goes above 3.7 volts when it peaks out on that first peak. If it doesn't get above 3.7, we unplug it, let it cool off, and we clean the heated wire element with brake cleaner. Use nothing that leaves an oily deposit to attract more dirt. But it can be true of any manufacturer. They all get dirty airflows at some time or other. Know what's normal and make sure you verify that. They're a frequent source of off-idle, light-load, lean air codes. It runs off B+ ignition power. It has a separate ground. It's got a ground there. It's got a ground for the down on pin 3. Make sure both grounds are working good. They've got to be under 0.05 volts. Normal is 20 to 30 millivolts, so we've doubled the value we normally see. Then the TPS, same type situation. Got a spec. Does it read normal value? Now what this is telling us is that frequently we see people opening the throttle stop screw to raise the idle so that the idle air counts are normal. When we do that, on this particular GM, we go above the 0.55 to 0.65. That tells us someone's opened the throttle. They've opened the throttle because the throttle is dirty. If the throttle is dirty and the intake manifold is dirty, the injectors are probably also dirty. Take as much information as you can get. When it's wrong, verify reference, ground, change the sensor if it can't read correctly. Coolant, got to read temperature. We like to use voltage. Get a specification system that shows you voltage. On this particular GM, we're looking for about 2.2 volts at 210 degrees, up to about 2 volts at 220. Remember, a lot of cases, the cooling fan does not come on to about 220. If you want to see what the real temperature setting is for driving down the road, take a recording driving down the highway on a cool day and see what your voltage is. You may find it drops well below 3 volts, which saying it's cooling off too much, needs a new thermostat. Common failure. Compare it to actual engine temperature. Make sure you know what you've got. Remember, these switch over. 120 degrees, a lot of them change voltages at that point and start over again. So that 2.2 volts, 210, looks a lot like 180 volts or 80 volts at 2.44 volts. Know which way it's going when you use voltage. Open circuit. Make sure it goes from between 4.6 and 5 volts. That tells us we have nothing pulling the circuit to ground. Then make sure we have less than 50 millivolts on ground. Any error then is going to be caused by the coolant temperature sensor itself. Same thing with inlet air temperature. Compare it to specification. Does it compare to actual temperature? What we like to do is close up the hood and let it heat up to the same temperature or approximate temperature of the coolant temperature sensor. Then it's the same test. Open circuit. Is nothing shorting at the ground? And ground is less than 50 millivolts? We have a good circuit. Change the sensor. Now, both lean and mixtures can cause misfires. If the engine is running too lean or too rich, diagnose the fuel system for control and delivery. And the EGR can cause the engine to operate an incorrect air-fuel mixture as well. Check for stuff causing that problem. All of these are clues to go look at, and we've shown you some data that you should be looking at for all of your diagnosis. The first question to ask when the engine isn't fueling correctly: do I have too much air or too little fuel? What causes too much air? I could have a vacuum leak after the mass airflow. Do I have too much fuel and too little air? Do I have a miscalculation where I'm delivering more fuel than I need for the air I've got? Remember, vacuum leaks can cause high idle conditions, but if they're excessive vacuum leaks, cause the high idle you're looking for. But you always check the IAC PID to determine if the PCM is correcting for a high idle speed. The IAC counts will be very low, less than 10 in most cases. Check for normal fuel control by looking at the fuel control PIDs like we just went through. Compare each PID to specifications. Know where to go if the reading is wrong.